in more higher dimensions, a surface. And that is very interesting because unless the points literally are right on the curve, there's some scatter, there has to be some sort of an estimation process to do that. And you not only want to know what the sort of, quote, best curve is, but you want to know to some degree how reliably you've estimated it. Now, if you know the parametric distribution, for instance, from astrophysical theory, that you know it's a Lorentz profile of an emission line or something, or you want to assume that it's something heuristic like a Gaussian or a power law, something simple, then this talk does not apply. It's the next hour. Then it's called regression. Okay? And here we're making no assumption of the parametric form, and so it's actually called non-parametric density estimation to make that clear. So the kind of place we might want to do this is we have galaxies in a rich cluster. We want to know the underlying distribution of baryons. We have lensing of background galaxies. We want to know the underlying distribution of dark matter. We have photons in a Chandra X-ray image. We want to know the underlying X-ray sky emission. We have clusters of stars in an HR diagram. We want to know stellar evolution isochrones. We have X-ray light curves of a gamma ray burst afterglow. We want to know temporal. It goes on and on. I mean, you can do 100 of these. Okay? Anytime you have data and you want something smooth underneath, but you don't know the functional form. Now, just to give you an idea, I think these people would say they think they know the functional form. It's called the NFW profile, Navarro-Frank-White profile, a couple thousand citations. But they don't actually know that. Okay, that's just an estimate from the density estimate actually from a simulation. So it's not actually based on theory. Okay, so one way of doing this, which isn't quite smooth but is very often done, is to use histograms. So here's some data. This is real data, and here's histograms with fixed bin widths. Here's with fixed numbers of objects per bin. Very different appearances. And one of the problems with histograms, there's a lot of problems with them, is you don't know what width to choose for your bin or what algorithm to choose to bin them, or you don't know your starting point. I mean, you can choose the lowest value, but you don't have to. And those three uncertainties, arbitrary choices, are enough to make histograms undesirable for inference. And the first chapter of a typical good book on non-parametric density estimation starts with histograms and then says don't use them. And then it goes to chapter 2 and tells you things to use. Okay? So astronomers are stuck on chapter 1 of the text. Not always, but often. So chapter 2 always is called KDE, kernel density estimation. And we actually know this. It's commonly used by astronomers. We basically, I think we would use the word convolve our data with a kernel. And the kernel has this is the distance, the exabyte are the data points. H is this bandwidth. It's the equivalent of the width of the bin of the histogram, and this is a normalization. And here's some rules about what this K function has to be. It has to have certain mathematical properties to correctly estimate the underlying distribution. A good choice is to use a normal kernel or Gaussian kernel. We often do that. A boxcar is not a good choice. But the best choice is called Ipanechnikov, which is an upside down parabola. Okay? The word best, these are technical things. These are questions of sort of power and reconstructing distributions with theorems behind them. But it ends up, the uniform is quite poor, the triangle is better, the Ipanechnikov is best, but the Gaussian is 92% as good as the Ipanechnikov. So I would say normal kernels are perfectly good. 92% is good enough for me. Okay? Much more important than to choosing the shape of the kernel that you convolve with is the bandwidth, that H. And it's actually quite difficult to know. And there are entire books. Most of the books on density estimation are all about bandwidth selection. And there's no simple answer. There's no perfect answer. A common choice by statisticians is to minimize a certain least squares type risk function called the MEAS, the mean integrated square error. And here it is. So you want to minimize the expectation, that means the average, of the integral of the square distance between the smooth data and the original data. And this ends up to be equal to the bias squared times the variance. And the bias squared goes as the fourth power of the kernel width, and the variance goes as 1 over that. And these two, you can see that that's a very strong function. It's very easy to find an h that minimizes this sum. Okay, there's only a single value that minimizes. And that's the h you choose. Okay? Is that minimizes the Mies or the MSE or the MAS. There's several variants of it, but they're all fairly similar. And there are theorems behind this. It's not that it is the only answer. It's just this is a common approach that is plausible. Just to give you an idea, astronomers are probably more familiar to minimizing the variance, but don't realize that there's a bias problem. Okay, and one way of phrasing it is if you choose big broad bins, you get a lot of counts in each bin, and you have very little noise, so your variance is down. But the big broad bins have missed the features of the variation, so you get a big bias. You little tiny bins, well, you get all the features, but you have a lot of noise, and so you gotta balance the two. It's not one or the other; it's both that have to be considered, or at least that's the most common way of approaching bandwidth selection.
Particular bias of something.
The word bias is a mathematical term. It is a formula. Okay, it's certain things of expectations. Certain things go to infinity, do not equal certain things. And it's full of theorems. Okay, I'm sorry.
Okay.
I'm not too good at it. I can tell you the book. Okay, Larry Wasserman, All of Non-Parametric Statistics, has the theorem made for grad students who are not in the field. In other words, for you. And for you, not just grad students. Okay, so I mean, you can read books on this. But I can't do the theorems myself. If I were to lie, I would say, oh, I don't have time to do the theorems. But the honest truth is I don't understand the theorems. Okay, I'm not a very good mathematician. Okay, so it ends up the choosing of the h is very, very important. Here are some what are called they're called rules of thumb that minimize the Mies for certain sort of common situations. And you can see there's that 1/5 law that 10 to the 5 times power based on the size of the data set. And this constant has to do with the standard deviation or the interquartile range of the data. So if you just don't know anything, you can choose Silverman's rule of thumb. Here it is for 1 dimension. Here it is for p dimensions. And this is, for instance, coded up as the sort of the default option for kernel density estimation in R. Well, there's many kernel for at least some of the R codes. A little more sophisticated way than sort of just guessing your way forward is to use your data itself to try to estimate what your bias and variance is for the best bandwidth. But it's a circular problem. You need to know the function and its second derivative in order to evaluate that formula on the previous page. And so what you do is you hold back some of your data. It only works if you have a large data set. Hold back, put in your pocket your data. In fact, you can even put in your pocket 90% of your data and do it on just 10% and do that 10 times. Or you can use n-1 points and leave one out. And there are all sorts of variants of this. But apparently some powerful theorems were written in the 1980s that this sort of, it's sort of like a bootstrap, but the purpose is not confidence intervals. The purpose of it is bandwidth estimation, and there's several varieties of these things in likelihood theory that are asymptotically known to be effective in many situations. And so there are procedures for choosing bandwidth that are not guesses. So often astronomers are taking fixed width histograms and guessing a width that's convenient. And what I'm saying is they can smooth it using some mathematical procedures that are generally effective, not necessarily always effective.
So there's, I mean, just going between the histograms and the optimal smoothing widths.
Right.
I mean, there's also theorems that give you what the optimal bin width is, right? I mean,
Yes.
they're related, right? I mean,
Yes. Right. But they don't want you to do it. One thing is that you don't know where to evaluate within the bin if let's say you're going to do some regression or something like this. And this business of the square root of n, which is really our motivation for doing this, is to keep that square root of n. You'll see in just a minute that they will give you now, this was not classical result, but newer results, they will give you heteroscedastic confidence bands for smoothed curves. Sure. And that's important, okay, and relatively new and coming up. Okay, oh, there it is. For large samples and simple PDFs, simple behaviors, it doesn't wiggle too much. Confidence intervals for normal, that means Gaussian, kernel density estimates, can be obtained directly from the central limit theorem, which means you can do it analytically for large samples. And for large or small samples, you can get confidence intervals using bootstraps. Often, not always perhaps, but very often. And so confidence bands can be obtained. Now, closely related to, let's just say, one-dimensional or two-dimensional smoothing is something called kernel regression. And we'll be covering regression, more parametric regression in the next hour. But this is non-parametric regression, which sort of is a non sequitur because regression needs a formula and non-parametric has no formula. Sometimes it's called semi-parametric regression, so it's not so contradictory in its label. But it has all those names. Also called local regression, which is perhaps the best. Okay, so kernel regression is a variety of local regression, and it's a way of saying locally we're going to fit. Usually they choose a line or a parabola, some sort of a simple polynomial, locally, and they follow the data along in its behavior, using so that the overall behavior is non-parametric, but locally it's parametric. And here's a famous one from the 1960s. The Nadaraya-Watson estimator. There's the Gaussian kernel. There's your data. Notice it's extremely simple. Okay, it's very easy to compute and very easy to sort of visualize what's going on. It's a direct estimate of the y's values. So there's some y values and there's some x values, and you can see their scatter, and then you can see the green curve is the estimator, and the green curve is the truth, and the red curve, which has some wiggles in it, is the estimator. And there's the local window with a Gaussian function or an Epanichev curve. It looks like there that it's evaluating it at that point. This particular picture is from Wikipedia. Okay, Wikipedia is really great. Wikipedia has everything I talk about it just about is on Wikipedia. Here's another example. You can see that the 95% confidence band is not always the same width. It's narrow when there's a lot of data that's well constrained, and broad when there's fewer data or more scatter. And that's what you want, okay? What you want is good estimates of confidence bands as well as good estimation. So here is the Wikipedia page for Loess. Loess is perhaps the oldest and most well-established of the local regression models from the 1970s by William Cleveland, who's written many books about this kind of thing, and it's very similar. And then there's spline regressions. Splines, again, they don't go through all the data points. What they do is you set what are called knots, K-N-O-T-S, at certain x values, and then at those points you evaluate the function, and you go through and you do polynomial or something regression, like a cubic polynomial is commonly done. There's a whole lot of splines. In fact, R and CRAN have like 20 packages on splines. It goes on and on. There's a whole lot of it. Here's a lovely essay by a professor from Carnegie Mellon. The problem has been you don't know where to put the knots. And so if you put too few knots, you get this dashed curve as a spline through this data, and it's a terrible fit, okay? And if you wanted to do it by hand, you'd probably capture that sharp thing with a lot of knots, and you would get this one, but you had to manually interfere with that, and then R does a lousy job by this, Cass argues, in its standard spline thing. So he developed an adaptive spline so that when you have rapidly changing data, then you change your bandwidth essentially, but it's not called a bandwidth with splines. It's called knot locations. So there are all sorts of strategies for locating the knots in spline that have made splines better than they used to be. His is called bars, or Bayesian adaptive regression splines. and he uses Bayes' theorem with MCMC to locate the knots. I'm going to show you not this one, but I'm going to show you another one that uses the Akiyiki information criterion, which is a likelihood measure for selecting knots or pruning knots, which is another way of doing it. Both of them, I think, are valuable. And look at this nice success he got. He fit this very sharply changing Poissonian data set. It looks like a Chandra flare, okay? Tick, 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 but it's probably neurons, okay? Neuronic data, I don't know, some sort of, they don't use astronomy for their data sets, okay? So this is just an example of a fine thing. Now, he happened to have written an R package, but didn't put it in CRAN, and I don't know why. So it's a little irritating that bars is not in CRAN to me. So to finish this very brief lecture on non-parametric density estimation and non-parametric and local regression, astronomers just tend not to just know much about this thing. So they tend to do parametric regressions and histograms and not realize that there's these other approaches. And some of the issues, particularly about non-parametric regressions with local bootstrap confidence intervals, really are very effective in following the data, but smoothing it and giving the confidence bands at the same time. And when you get all that, then you don't have to assume it's a, assume that it's a linear function. You follow the data. It's really quite nice. Okay. So some of them are well established, they're decades old, and some of them are relatively new. There's a whole bunch of books written in this field in the mid-2000s that show that it's really quite a young, there's been a lot of recent progress in a lot of young fields. Okay, ladies and gentlemen, now is our time to crank up our computer and find our R, which I don't know how I lose my R all the time. So you'll have to excuse me a second. Okay, get an R console going. You can choose a fresh one. Every time you leave your R console, you either click the red dot and just close it, or you say quit or Q. See, Q with parentheses, that's a function to quit. And it will always ask you, do you want me to save everything or throw it away? If you save everything, it goes into a sort of like a history file, a bin. There's also a history file of commands called .rdata, which it hides somewhere on your computer. I've never been able to find my RData file, but it can get rather big if you keep on saving it over and over again. You can get hundreds of things that are in there, and you got to clean it out once in a while. Or else you just don't save it. And you just say, oh, well, I enjoyed my stuff, and now I'm just going to throw it away. And that's what I've assumed you've done here. So the first thing I want to do is just to regenerate that XY data set that I put in this morning. If you remember, it was the scatter itself depended on the variable, and it had some weird curvature in it. And it was just like an interesting data set to practice with. So now we can run a KDE on it. So I tried to find out over lunch how many. I couldn't. I'm guessing 20-ish of the original CRAN packages are now put inside of base R. And when they're put inside of base R, you don't have to bring them in from a distant mirror. They're already there. But you have to say the word library. And you have to know that it's there. And I have no idea how you learn what's in R. It's so big and so confusing. Their indices are poor. So you just have to trust me that kern smooth is already in, and it's a capital K and a capital S. And if you don't put the capitals in, you won't find it. So this ends up to be, Wand wrote one of the major books on density estimation and has one of the major codes, which is now in its 23rd version here. And so this is an example of sufficiently well established that the R core team has put it in base R. So you can rely on this as doing a good job.
What is library kern smooth doing?
It's bringing it into your current session.
Is it bringing in this function called DKE?
No, it's bringing in an entire package. So thank you, Tom. That's an excellent question. Let me show you how do you know what's in a package. And so I go to Google. Excuse me a second, please. It worked a minute ago. I go to Google. Okay, I can't do it. Go cran, kern smooth, and look at the PDF file, and that will tell you what's in the package. And at the moment, I don't seem to be able to do that. So inside of that, in that package, is a help file, which I can look at here. BKDE in 2 dimensions. Except I got to spell it right. Okay, compute a 2-dimensional binned. Oh, that's what the B is. The B is binned. Kernel density estimator returns a set of grid points in each coordinate direction, and the matrix of density estimates is a standard bivariate normal density. And the tricky is what bandwidth you put in. Now, this is not the most sophisticated program. I'll show you more sophisticated ones in a minute. This is from one of the early slides I showed where there's just a constant h put in. And so the constant h I want to put in this case, is going to be determined by a program called dpic. And what is dpic? I don't really remember. It selects a bandwidth for kernel density estimation from the same package. And dpic means direct plug-in. That's some jargon for a mathematical method. Okay, I frankly can't explain it. I don't know enough. Okay, but this is it's one of those rules of thumb that I referred to earlier. The rule of thumb is that I need 0.2 bandwidth in X and 0.05 in Y to get a reasonable smoothed density estimator. So it actually, let's just take a look and see what is inside of SMXY. So structure SMXY. It has a 50 by 50 grid. That's a little small by my standards. And then F hat is the estimator. A hat means estimator in statistical jargon. And we could now take a look at that. In fact, I think I don't like that. Help B. I know what. Go up a couple times. I want more points. Grid size. I don't want 51. I got a big computer here. That's ridiculous. Okay, so I'm going to go up and change my parameters here because I'm just irritated at the default. Grid size equals concatenate or combine. I'll say 300 by 300. And that way I'll get more resolution. I get the same there. I have a bigger grid. And now I'm ready to display my grid. And it actually is an image. I mean, it's a 3-dimension, it's X and Y and it's a value. So I'm going to use a program, a function called image that displays these things. And there it is. So, yes, there's a typo. SMXY, one of these three has a typo in it. Do you see there's an extra dot or in your code, an underscore? That was pointed out to me. Is Warren in the room? Thank you, Warren. But I was unable to change it for everyone, but I appreciate you finding the bug. Okay. So I personally corrected it, but you didn't. I couldn't for you. I do apologize. And I just wanted to remind you from yesterday, this is what the data set looked like. Do you remember that funny data set that looks like that? And now this is the density estimator for that. And since I have random numbers in there, the data set I have today is slightly different than the data set I had yesterday. So my outliers are not on the same spot. Okay, so I did a smooth density estimator. Thank you very much. That's pleasing to do that, but that was a rather traditional one with a fixed heuristic rule of thumb bin size that minimizes the me's only under certain conditions. Let me just show you a couple things one could do with images.
So is this basically like a 2D PDF?
It's a 2D estimator of the PDF. That's correct.
Okay.
Right. I can put contours on an image like this. There's some contours. The contours are actually labeled. I can turn the labels off, but it actually tells you the levels in surface density. And there's many color palettes you can use. And then here's another program that allows, oh, wow, that's terrible. That came out much better before. I wonder why not. You're right. That's hilarious. I actually ruined my perspective plot by doing the high resolution. That is really funny. That is just hilarious. Thank you so much for that quick insight of yours, by the way. Okay, so I'll go back to something more reasonable here. There. That's prettier. So I chose an angle to look at it, and I chose an angle to shine the sun on it, so it has shadows. And this is a typical three-dimensional graphic, okay, visualization of, in this case, I don't care much about it, the science, but the point is that, and I'll be showing you a couple more sort of three-dimensional type visualizations in I think, on Friday.
Was that estimate, the rule of thumb estimator, take into account if it was varying on a much higher spatial frequency?
No, that's one of the reasons it's not so good. So that was Roman numeral 1. In other words, that was a standard constant bandwidth. And it's not so great. It's not nearly as complex and interesting as Bayesian adaptive regression splines that pays attention to the local variations. So it's not adaptive. Okay. So let's, and those adaptive works are fairly recent. They're not, we often do adaptive smoothing in astronomy. You should be aware that adaptive smoothing is not a well-developed field in statistics. In other words, it's not in even the advanced texts often. And that another reason is that there are no good theorems for it. So, they write texts on things they have theorems for. When they don't have texts, they tend to not do it. So when we do adaptive smoothing, be aware it's not as well founded and rooted in mathematics as a lot of other things. And that's interesting. That's why I'm so interested in when someone as distinguished as Robert Cass writes a Bayesian adaptive regression spline, we should pay attention. Okay, so let me go to Roman numeral 2 and see if I can do something else that's not as simple as a constant thing. Okay, what did I do this time? I did something totally different. I did linear modeling, LM. And actually, for most people who are using R, LM is extremely important. There's entire books on just teaching biologists and people like that how to use LM. It's a very, very big and important program. It says I'm going to model Y as a function of, in this case, I've decided to do a quintic polynomial of log x. I had to define my log x's ahead of time. The tricky thing, not the tricky thing, but the very important to realize is this little tilde. The little tilde is very important in R. The little tilde means that this is what's called a formula. And the word formula is very specific to R. It means something very specific in R. It means that you have a single response variable, log y, is then dependent on in a linear fashion on a whole bunch of things here. And I'll show you, give you a little lecture on this in the next hour on what linear modeling means to statisticians. But this is the implementation of linear modeling for the moment. So the product of what comes out of YFIT is of linear modeling is a object of class LM. Sort of could have guessed that LM would make something of class LM, and that it's actually quite a complicated product. This is what I meant when I said some programs make rather complicated lists. This is a list, an R list. You put you say YFIT $ coefficients, and you'll get the 6 numbers from the quintic solution. You say YFIT $ residuals, you'll get 500 residuals, effects, rank, fitted values. Fitted values is quite important to us. That's the actual function itself. You know, the values of the function at the 500 points. And it gives you stuff you're generally not interested in, sort of internal results of some matrix decomposition it did while it was computing things. Oh, it tells you how many degrees of freedom. It's sort of nice. And it tells you what function you did, just in case you forgot. Yeah.
Could you have your screen at the map so I can see this as well as that?
Yep.
Because I'm
Yes.
running a bit.
Yes, one of the problems is that I have a very low resolution, projector. And I have a desire to keep the letters large so you can see it in the back of the room. And the net result of all of this is I'm much more crowded on my screen than you are. You have a bigger screen than I effectively do also. So this is a well-known problem for presenting anything in a tutorial using projectors. Why we don't modernize projectors is beyond me, but that's it. Okay, so let me now plot to see if I can see what this particular parametric model did. Well, there are my data points. Now I'm going to use the R function called lines, which, as you might think, actually puts the data in, draws lines that go through it, and that's my polynomial fit, 5-order polynomial fit to this data. So this one's a parametric regression, not a non-parametric regression, because I globally told it to fit the whole thing globally with a fifth dimensional polynomial. And I don't know. You can choose to say what you think about it. There's a couple little tricks here. Plotting the points is easy. I just took the logs of the x's and log of the y's, and I plot it with solid circles with a gray color with a small size. And that's a standard plot. That's how I got the gray dots. The lines, I figured it ended up that the results from the fit were it's in a bad order. The x's were scattered, and it likes to draw lines from left to right. So I had to sort the x's, and then I had to use the order of the sorted x's to sort the y's. And that particular piece of syntax took me a little bit of time to figure out. I had trouble figuring out the difference between sort and order. This one gives the index, and that one actually sorts them. And that was a little trick that I finally learned as I was writing my tutorial for you the other day. And I'm going to copy this onto my disk in an EPS file, and you will find that this perfect plot is there. And if I want to make it a flatter plot, notice it automatically changed the density of the labels. Yeah, that's not a bad one. There, that's the one I like. Okay, so you can manipulate particularly the quartz window is really nice for manipulation of the appearance of graphs.
Sorry,
Yes, sir.
question. In your plot there appears to be a glitch on the left-hand side where the curve's not smooth. Is that just a plotting?
No, that seems to be the Sorry, excuse me. Yes, it's because I did lines. And lines is drawing straight lines, and that's the first point, and there's a big jump to the second point. Yeah. So, guess. In this case, I created it mathematically. In other cases, I would read it in, and we will see soon. We'll read in real astronomy data sets. So that's coming up. So I'm still in the sort of hypothetical data of things. Okay, now I had mentioned splines in my very, very brief lecture. So let's take a look at a couple splines. So one is built into R called smooth.spline. It's into current smooth, I think. And there's a cubic spline there. In fact, I wonder if I can get these things to pile up. Where is my... I don't seem to have it here. Why don't I go ahead and do it myself? Par mf rho equals C. You don't have to do this. I'm just going to put two panels together here so I don't keep on having to change windows or whatever. Okay, I'm on the section called Roman numeral 3, called two spline fits. So I ran smooth.spline, which is a function. I can help it and find out which one it's doing. Help smooth.spline. It ends up it's in stats, which is part of base R. It fits a cubic smoothing spline to the supply data. And there we go. I can read all these options. How many knots are being used? That's the tricky thing, is the knots. In this case, I decided I wasn't smart enough to choose anything. I just said, no, do what you normally want to do. And it did. So the first thing I did is print the points again. There they are again, same points as before. Now I'm going to oh, I see. I decided I didn't like that one because these two outliers were annoying me. So I decided to plot it again with some limits and also to get my titles right. And I just wanted to make a prettier plot, basically. So here's my prettier plot that okay, of the data. And now I'm going to take the lines from the output of smooth spline and run lines on that and show that on the data set. And there it is in green. And I sort of like this better than the Quintic one because it didn't wiggle over here on this side. It didn't create these, what I thought were fake wiggles, but also didn't really grab that rapid rise particularly well, I thought. It didn't dip low enough and rise high enough. So I wasn't that pleased with it. But what do I know? That's what this particular mathematics did. And then I want to show you a very important function in R called predict. And predict is used for all things like linear modeling, all regressions, all splines, all many, many inferential processes. It will produce a class object that allows predictions to be made on new values. So let's just call it an interpolator. And so here I said, well, give me a sequence of evenly spaced values from -2 to 0.4 here and there, and tell me what that solution would predict for those values. And it's very good for plotting and for bringing out useful information out of unevenly spaced data. It basically it smooths your data and reports it back in an evenly spaced data set. So then I was curious as to where the knots were. So I had to go deep inside the output to find out where the knots are. And then I put them at the bottom of my plot in dark green. And then I realized, oh, I really don't like this program. I mean, that is ridiculous. It shows hundreds of knots, particularly in this curvature area. And there's not that much information there to sit there and do regressions on little teeny, weeny scales there. I thought that was a really poor decision by this program. And this is what people were complaining about splines for many years, is the algorithms for knot selection were sort of dubious in many cases. Here's how I got them. I found the output of my spline, and I was inside of fit, and then hierarchically inside of that were the knots. And how do I know that? I had to read the help file to find this. So I had to read the help file to know how to pull out some of the more detailed information from a fairly complex code like a spline regression. So I actually decided I just didn't like the philosophy of this green line. I just didn't like it. So I found another one. I found constrained B-splines non-parametric regression quantities. So by the way, I actually wrote it here in the comments. I looked at the help file. I said, where does this code come from, the one I didn't like? Well, it ends up, it comes from two of the most distinguished statisticians in the world, Hastings Tibishwani from Stanford. So these are not slouches, they're very famous, but it's a very old code, and the code was written by Finbar O'Sullivan, and I looked him up and I found out he's chair of statistics at a university in Ireland. So, this particular cubic spline fit has a good heritage. These are distinguished scholars who wrote it. It's not a bunch of kids. So I certainly can't complain that it's being done by amateurs. I'm just complaining that I don't think doing regressions on such small scales is a good idea for my problem. So I looked around, and there's dozens of spline codes and packages in R and in CRAN, and I found one called Constrained B-Splines Non-Parametric Regression Quantiles. Quantiles is good for when you have uneven distributions of your scatter, and I certainly have that. I put it into the data set. And then I found out that, okay, there's some mathematics written. This is pure mathematics in ACM Toms, which is a distinguished journal. And this guy wrote an algorithm for making quantile splicings in a journal in 96. And then 99, he wrote this code. And in 2007, he's one of the founders of our, wrote a fast and efficient implementation and put it into R in another journal. So I would say this is a fairly respectable heritage of a code. I must admit I've never heard of Ung to know if he or she is distinguished, but this is not by children either. This is a serious effort in applied math. So I decided to try it out. So now, ladies and gentlemen, is your first time that you are being asked to bring in a code that is in CRAN. So I'm bringing you up a notch in the tutorial. So all please type in install.package. Oh, quote cops. I apologize. Quote cops. And a little tiny window will appear that gives you all the mirrors. And because we're all here, I want you all to choose a different mirror. So just randomly choose one in, I don't know, Argentina or in Nebraska or something like this. Now, I'm a little unsure why I'm stuck. Are you stuck? Or are you downloading it correctly? Excuse me? It works. Okay. Does anybody know why I'm stuck? My wireless, yes, because I'm a visitor. They keep on logging me off. That's my problem. Right. Harvard guest doesn't like me. Right. If I'm a guest, I'm only a guest for a few minutes. I see. Okay. Right. Okay, ladies and gentlemen, you're seeing an embarrassed presenter crashing R. I'm not going to report it. I'm much too embarrassed to report this. You'll have to forgive me as I try once again to bring up my R and recuperate. Talk among yourselves or proceed with library. You do install that package to bring it into your sort of the R infrastructure, and library brings it into your current your current session. Okay, I'm back online. So, you can do help COBS and read all about it and find those references that I just told you about. And the tricky thing about this particular method is that it uses maximum likelihood theory, just like Cass uses Bayesian theory for knot selection, and it deletes unnecessary knots or knots that it doesn't believe are needed using the Bayesian information criterion. I'm sorry, I'm still a little lost due to my crash. 1 second. Okay, I'm ready to put in my lines here. Okay, there we go. My red line is now my new constrained B-splines fit. And what's important here is that I get other capabilities of getting quantile fits. And now you'll see that it did the whole thing with only 2 knots, which I thought was a little sparse, but that in fact is interesting. It's actually fitting a parabola and a parabola and a parabola. It's only fitting 3 parabolas. And it decided that everything you could know about this, according to sort of the information available through the likelihoods, is actually known by only a couple parabolas. And that's rather interesting that's what this mathematics sort of told you. And it really showed that this instinct I had that there was a lot of information up here, I was right. There isn't much information. And once again, the 25%, the 50%, the 75%, these are confidence bands. These are estimated. You can see, of course, that they're not that local. But this is not a silly program at all. And we've now submitted a paper to AppJ that uses COBS because I felt it was parsimonious in its use of information. It's a local regression method that didn't overfit, essentially. So I thought that was pretty good.
Did you check them out with many different types of data sets?
No, I didn't.
Well, I mean, could it be that one kind is better for one?
Okay, the answer is there are books and books and books on splines that help you guide you through whether or not smooth splines or B-splines or flat splines and plate splines. And they all have some theoretical values that are good and bad. I frankly haven't read all those books, and I'm only slightly familiar with the issues. Spline regression goes way back to the 80s, and there's a great deal to know. My own personal opinion is I think it's good to know something about splines, but I'm not sure you need to know all of it. Splines fell out of favor, I think, because the knot selection problem irritated people. Okay, but now there seems to be, through Akiki, Bayesian information criterion and Bayesian selection, some improvement in that particular aspect of things, and that's not, and some of it is of the improved work is now in R or CRAN. Okay. I'm now going to talk about 3 well-established local regressions. That means you go along and you do, usually it's little parabolas as you go along the data set. The famous one that dates back to the 70s is William Cleveland's Loess, which also has a robust option to it that he put in the 1990s. So it is a second degree little parabolas. It has Gaussian windows. It's an interpolated method. It has to, some sort of a binning is involved. I have 500 observations. And it found, interestingly, it found that it's equivalent to only having 6 parameters. So it again also found, essentially used only 3 or so, approximately 3 parabolas. So it didn't overfit either. Here's the data once again. And here is the lowest fit. Let's take a look and see what we like of it. So the lowest fit is local. So it really can have jiggles in it. And it jiggled right there. See the little jiggle there? and that's sort of interesting. You know, is that jiggle real? Well, I don't know. It's, quote, following the data. In my opinion, it didn't do the world's best job at this little turn right there. I missed it, the last very beginning. And sure enough, almost all of these splines and local regressions have difficulties getting rapid changes, although that's what Cass believes his bars addresses that better than others. And once again, I can predict, create a little sequence of evenly spaced numbers, use the predict function of the solution of my local regression, and put that into a file. Let me just take a look at it. There it is. I've got 100 numbers of the values, 100 evenly spaced numbers that represent this red curve, and I'll put that together into and put it into a file and write it onto my disk. I row binded it. Oh my. I think I should have had cbind there. I think that was stupid. I think I really want cbind. I want to column bind it. So the first column is the value of x. The second column is the estimated value. And I'll put that into a simple ASCII file, or I could have put in a binary file onto my disk. So again, it's important to be able to bring graphics out of R, but it's also important to be able to bring tabular information out of R as well. Just because I want to preserve it, and maybe I want to read it into some other program. Maybe I really want to live inside of C or inside of IDL or inside of Python, and I just want it to just run just my little local fit in R, and I want it to live somewhere else. And there's nothing wrong with that at all.
You were right for the R bind, because I just did C bind and it seems to be almost like this.
I wonder why R-bind is right. Okay, thank you. Oh, I had R-bind with n col equals 2. That's the way I did it. Okay. I guess that was the way I chose to do it. Thank you. Okay, now I'm giving you a second well-respected local regression, non-parametric, semi-parametric local regression technique. It's called QuantReg. It's in this book here. It has a lot of mathematics behind it that's quite difficult. You can go ahead and install the package and then say library. And I found that it crashed on me, and I found out that it wanted something called matrix models, so I brought that one in. Whoops. Oh no, not again. I just screwed myself up again, sorry. I have. Yes, the stop button will work under many conditions, but this hanging is too difficult for it to deal with, so it didn't deal with it. I've actually wondered why I can't stop things a little more gracefully, but it's also true that R doesn't seem to mind crashing, and if you keep your script on a separate file, it doesn't really matter. The history file is all available to you, so you can recover your past work. So I'm not saying I advise crashing, but it's not a desperate problem when it happens. Okay, oh, I see, I have to say this. Okay. Some packages load in other packages. Okay, I personally have recovered from my crash. I'm on quantile regression near the bottom of our density estimation script. So I've plotted in a sorted way the data, and now I'm going to plot the 25%, the 50%, which is the median, which is most people want that one, and the 75%. Oops. I think this would work. There we go. And I've done that, and this is interesting. Quantile regression, in this case, I did linear quantile regression. I could have tried nonlinear, and so it fitted 1, 2, 3 lines. It decided that there were 3 lines to draw. Again, there's really not that much information in this distribution. One shouldn't try to fit a million things to it in this case. But the interesting thing is it tells you something about the heteroscedastic spread of the data around the best local fit. So this is QuantReg. Yes?
I have a question. So, for people who think about parametric fitting, so when I look at this...
Yes, that's coming up in a few minutes.
No, but if I look at this,
No.
is there a way to say the slope of this?
Yes, yes, all of those are available in the output, in the list file.
Okay.
So you do help on RQSS, and it's a rather long help file, and it will look at the value part near the bottom and find out where the coefficients are for these, and then goes to structure, STR, of your output, little thing that you assigned to be that, and go find it, and then print it out using the $sign to get deeper into the list. Yes, everything is available to you. It's not magic. The only way the plotter knew to plot it was available. In fact, I can even tell you where it is. It's under fits. This is what I personally call it. That $sign coef 1, and then for some bizarre reason, it's -1, and I don't remember why that's true. That is strange. No. I have to read the output file to find out what I'm doing. But at one point I did read it, and I carefully designed this. I may also have looked at the example, and I may have learned how to do this from the example with these -1s. And also there's a book. He wrote a whole book on how to use QuantReg in R, and I may have read the book. And I didn't say it's easy, okay? Okay? It's not necessarily easy, but it's there. Just a little thing. Springer has 50 volumes already, and they're all on something called Springer Link. And if you happen to have Springer Link available to you, you can download all these books. But if it's in a different publisher, like CRC Press, it tends not to be easily available. You've got to go to a math library, and it's more of a pain. So excuse me for the little side.
What if,
Sure.
what if the data was really a picket fence of narrow features?
You'd have to see how each one of these did. First of all, in some of them, like William Cleveland's Lois, you can actually specify a smaller span, like the bandwidth. You can tell it, please look at your data on very small scales. And it will go and wiggle around and look at it on small scales. You don't have to use the default. It's doing a default of some sort of a plug-in estimator usually. And you don't have to do that. You can go ahead and tell it what you want. You can tell it I want 7 lines there, and it will do 7 lines. So you got to read the help file of each and every program. They're not consistent. They're not consistent with each other mathematically. They're not consistent with each other in terms of how the code was written and what the inputs and outputs are. Because each one was written by a different team of typically statisticians, and some of these represent substantial efforts over many years. And I happen to show it to you in only 5 minutes, but they're not written in 5 minutes. Okay? And then they write a book on their code. And they have articles in journals that precede all that. So, I mean, you're looking at years of research in computational statistics.
Is there a measurement of how adequately the data have been fit with the different
Okay,
models?
why don't we talk about that in a few minutes when we do regression?
How do I know if I don't know what my data should be, whether this is correct or the original?
Yep, I sort of agree. So this, let me take you to the very last one, which is NP, where the first author named Hayfield is now actually an astronomer from Max Planck Institute. So what I like about this one is it sort of addresses your question, Saku, and you can see it actually took a full CPU second to do it. Oh, another CPU second, and it gave another one of these estimators. Well, thank you. This one's another non-parametric regression. Actually, I thought it looked pretty good. A little too low there, maybe. But what I really like are these little error bars. You see them, little tiny error bars? Unfortunately, they're dashed, and they don't give options on how to graph it. And the error bars are very small here and pretty big there. And those error bars are from Bootstrap. And that is what I think very important. It essentially addresses the question you just asked. How well are we doing? The quantile one with 2575, it addressed it. And the Bootstrap error one is also addressing it. So some of them, the newer ones, are addressing what we really care about. You know, we don't want you to overfit. We don't want you to underfit. Maybe we want you to do adaptive as much as possible. And we want to have some idea of the reliability of your fit with respect to the data itself. And so none of them are perfect, and it's not easy to answer your question, Ed and Saku. How do we know what to do? In fact, one of the bad things about R and CRAN is that I've taken you from where, when you walk in the door, you know very little about non-parametric regression, and you leave an hour later confused because you know too much about it. Okay, or you have too many options and you're not knowledgeable enough to help choose. But even knowledgeable people don't really have ways of choosing either. So I don't know why thin plate splines are more preferred than B-splines. And some people will have different opinions on those things. So I can't tell you how to do your research, ladies and gentlemen, but I can open your eyes and give you tools that are wider and broader tools, and sometimes deeper tools, than you're probably familiar with. And to show you they can be implemented trivially. I mean, it's not very hard to implement them. But their meaning, I can't tell you I understand the meaning of all of them.
I was just wondering, can you not calculate a chi-square for each of these different cases and then decide
The word chi-squared is not a good phrase, so we'll go to that right now. Okay. So, why don't we say a goodness of fit criterion? Okay. And I would say that that's a very honest statement, and as long as you don't say chi-squared, goodness of fit, I would agree with it. Okay, I'm sorry, I'm now 10 minutes late, but I think it's time for a 5-minute break. And then those of you who wish to come back, and we'll talk for an hour about regression. Hi there.
My name's Cameron.
Cameron, yes, I've heard of you. Nice to meet you, Cameron. It's great to meet you.
I just got you an account.
By the if the eligible, that occurs when the potential energy is much less. just by the random motions of the temperature. Interesting aspects in the case in between. Magnitude as the kinetic energy. Found out consistent with the charge separation in units of the background electron density of the so-called Debye length to the length of the system